fails to give me the bandwidth I'm paying for. Yes, record. Thank you.
Recording in progress.
Okay. Now, we're looking at eigenvalues and eigenfunctions. See what that means shortly. And since you know about harmonics of a wave, you know that if we have a string between two endpoints, you have one harmonic that can be represented by this, and of course this wiggles back and forth. You have another harmonic that looks like this, and you can achieve these harmonics if you're at one end of the string just by nudging the string a little bit back and forth. You get this jump rope mode. That's your first harmonic. And then if you double your frequency here, you get this mode where one end is going this way, the other end is going this way. So the string kind of does this. And then you have a mode where the string does this, and so forth. So for every integer n, until you get down to, near the atomic level of the string. When you get down to that, you're not gonna get this behavior. You're getting into the quantum mechanical range, and then things with the energy dissipation, all kinds of things mess you up. So you can't go too high on this. And of course, we're doing it with our hands. There's a limit to how fast we can wiggle our hands. Take enough caffeine in the morning and get higher harmonics. But we have these modes with different frequencies, different energy characteristics, and so forth. And you'll remember some of that from physics. At least you've seen it. Might have been a couple of years. In your case, I know it's been 2 years. So, okay. So anyhow, we have this equation. Now, why this equation relates to this, I'm not going to go through the physics of it, though I'd love to do it. What are our solutions to this equation? Well, if you plug in y equals e to the RT, you get r squared plus lambda equals 0. So r is plus or minus the square root of lambda times I. Yeah, I'm just going to write out the solution. So it's going to be like a C1 cosine of square root of lambda t plus C2 times the sine of the square root of lambda times t. And all this is just very straightforward application. So I have left off the details. Okay? So we have a linear combination of the sine and the cosine. And of course, if we want, we can write this as a cosine square root of lambda times t plus phase phi. Okay, now, that's our general solution. Yeah, this is just a standing wave equation. It's the wave equation where you have two waves corresponding to this coming together, forming an interference pattern that is the pattern of this string, the oscillations of this string. or the amplitude phase model. Okay, well, you don't know what this means for a given string until you know the length of the string in the boundary conditions. Now, as you know, the boundary conditions can be the string is fixed here, and the string has length L. With fixed ends. They don't have to have fixed ends. Okay, you can have waves where one end is free. Okay, that's another problem. And you might remember how that worked. Okay. And of course, it's a homogeneous string with constant tension and all that stuff. And if you're dealing with strings, it's kind of hard to achieve the open end when you have homogeneous conditions. You can do it wiggling a string that's hanging down, but the tension in the string is no longer uniform because the upper part of the string has to support the lower part of the string, therefore giving you uneven tension, which complicates things considerably. But you solve that with a differential equation. It's just a much more complicated equation, or significantly more complicated. Okay, so anyhow, here's our solution. So boundary conditions. And you know, I did something a little bit stupid here. This is a steady state, not a steady state, but got to do this in terms of x. Now, I was talking about a function of t. You would, if you want to get the equation for the oscillation of the wave, you would then have to take the tension and so forth and figure out the velocity of propagation, so you can figure out the angular frequency. So you would multiply all this by like a cosine of omega t, okay, to get the string. This is the space dependence of the string. And we want to set this up where the y is a function of x. So we're really just getting like the graphs that we see here. We can set them in motion by multiplying by cosine of omega t, but that's a separate question. And we could incorporate all that if we just use the wave equation, okay, that relates the second derivative of y with respect to x and the second derivative of y with respect to t by the velocity of propagation, and we actually talked about that, I think, in your course to an extent. We're not doing that. That's a partial differential equation that actually reduces down to a couple of ordinary differential equations. We're not going to go that far, although I'd love to. There are other things we need to do. Okay, so we have, in any case, we have boundary conditions. Now I can write my boundary conditions since I've got this in terms of x and not in terms of t. Okay, boundary conditions are no displacement here, no displacement here, because your ends are fixed. Well, now we see that whichever form we use, we can plug in to these two conditions. This form is a little more convenient for these conditions than this one, because in this form we can see that phi has to be either pi over 2 or 3 pi over 2. Okay? And then we're going to find that our values of lambda are restricted. So okay, y of 0 equals 0 implies this. Which implies cosine of phi equals 0. Which implies that phi equals pi over 2 or 3 pi over 2. We can pick. So we'll pick the smaller. Okay? So naturally I write 3 pi over 2, pi over 2. Okay, so then y of L equals 0. What's that do? Well, that implies, knowing now that phi is going to be pi over 2, that y of L equals a cosine of square root of pi at square root of lambda L, thinking plus pi over 2 equals 0, which implies what? That and not equal to 0. Write things down with attention to what I'm writing rather than reflex, and I'll get it right. Okay, square root of lambda L plus pi over 2 was pi over 2 or 3 pi over 2. Now pi over 2 or 3 pi over 2, well, not just that. It could be any odd number times pi over 2. Okay, I'm going to regret not having washed that last board, I think. But if necessary, I can do it. So now we have the condition. It should be sticking. That square root of lambda L plus pi over 2 equals what? I'm going to write it as (2n plus 1 over 2 times pi), because 2n can be equal to 0, 1, 2, etc. If n is 0, you get 1/2 pi, and of course that's pi over 2. If n is 1, 2n plus 1 is 3, so you get 3 pi over 2. n equals 2, you get 5 over 2 times pi, 5/2 pi, and so forth. It could be any of these numbers. And of course, this number is going to determine which harmonic you got. Okay. So square root of lambda times L equals yeah. Somehow that didn't seem right to me, but that's just me. Had to check it out before I wrote it down and continued. Now I've got the problem. I've got a square root of lambda in here, and it's not right. I'm not sure why it's not right. I looked back and I found that, it seems to follow from the equation. Could be that the equation doesn't really correspond, because I think you need a lambda squared there, but if you've got a lambda squared, then your characteristic equation is going to become r squared plus lambda squared equals 0. Then r is lambda times I. And I think that's the equation that's going to correspond here. So maybe this equation doesn't correspond to the model that I gave you. Because we're going to get lambda equals the square of n pi over L. Okay, I didn't work through the physics of the situation, but I don't want to explain how the second derivative of the thing gives you the force and all that stuff. And the second derivative is time and all that. So I might end up having to do that, because it's kind of important anyway. Okay, anyhow, you get this. Which is then okay, this doesn't correspond to the string where clearly lambda, which is going to actually be the possible wavelength in that string, should be L over n, if lambda really is the wavelength. Now I have to go back and redraw the string thing. Okay? Not thinking that fast today. It's more like atomic orbitals, where you have eigenvalues that determine the orbital that are proportional to the square of your atomic number. And you wouldn't have an n equals 0. You'd start with an n equals 1 if you're going to use this model. First orbital, second orbital at 4 times the radius of the first, and corresponding energy levels that you get in the same way you get energy levels of, or the energy of a satellite orbiting a planet. Totally analogous. We didn't get into the atomic physics, but that's something you actually understand based on what you know about physics. Okay, so anyhow, those are our eigenvalues. Okay, so those are your eigenvalues, and your eigenfunctions or y sub n equals any multiple of the cosine of lambda x, which is going to be this. Okay, and that simply goes back to, here's the form of your solution, and it's a square root of lambda times x. And wait a minute. Yeah, this actually, okay, I had a brain freeze there. So there we have it, and actually this does correspond to the string and not to atomic orbitals, which is going to really, it didn't feel right. So the square root of lambda didn't feel right, but it works out. Doesn't matter what you call it. Whether you call this lambda or lambda squared, doesn't affect what you end up with here. And you can think through why that should be. Okay, so this corresponds now to let's make sure this has the right meaning. N pi over L x changes by pi write it this way, and again, think before I write. When n pi over L times your change in x equals pi, so that your change in x should equal L over n. Okay? And that's exactly what happens up here. Changes by 2 pi when this equals 2 pi. In other words, this goes through a whole cycle. Okay, when x changes by 2L over m. Okay, now what's that mean here? Well, look at this jump rope mode of oscillation. Here's L. What's the wavelength of this wave? You have to complete a cycle. So here's half a cycle, the other half goes out here, and the length of the cycle, the wavelength of the wave, is 2 times L over 1. That's your n equals 1 mode. Now I've got n equals 0, 1, 2 pi. Okay, this would be equal to n pi. I'm fudging a little bit. N equal 1, 2, and so forth. You can resolve that little discrepancy. It's not too hard. You want to think about it though. Okay, so if n was 2, then your delta x would be just 2L over 2, which is L. Well, that corresponds to this mode. Here's a complete cycle sitting inside of a string of length L. You know, spanning a string of length L. And then if n is 3, you get 2/3 of L. Well, this one right there is 2/3 of L. Okay, so this matches the string. And that matches then the string behavior. So that's one example of eigenvalues. Okay, you get your eigenvalues, get your eigenfunctions, and your eigenfunctions correspond to what happens to the string.